Hello everyone, this is Anand Ranjan, Assistant Professor, School of Computer Application, Bhamu Banarsidas University, Lucknow. Welcome you all in the video lecture series of Digital Electronics. In this video, we'll talk about the counters, which is synchronous counter. Okay. Synchronous counters. Am I audible?
Yes, sir.
Okay, so just similar to what we have seen in asynchronous ripple counter, in this counter we also have up and down counter. So let me write it: synchronous up and down counter. Okay, synchronous up and down counter. Yesterday we also have discussed few important note point regarding this. So let me write it. Number one, it consists of series of series, or better to write in this way, it consists of series connection of T flip-flop or if it is not T flip-flop, then other flip-flop converted into T flip-flop. This is the number one point. Second point is the T flip-flop in the LSB position operates in toggle mode, that is T is equal to 1 mode. This is second important point. And the third point is a flip-flop in higher significant position toggles when outputs of all lower significant flip-flops are equal to 1. Okay, equal to 1. And one more important note point also you have to write it here regarding the asynchronous up down counter. And this note point says that the counting sequence, this is very, very important. The counting sequence is independent of or positive or negative edge triggering. Okay, positive or negative is triggering. Positive or negative is triggering. Okay, it is clear.
Yes,
Yes,
sir.
sir.
Hello.
Yes, sir.
All right. So now
Yes, sir.
let's first design our 4 bit 4 bit series 4 bit series up
हाँ
counter.
हाँ ठीक है.
Up counter. Although there is no fundamental difference between the output you can observe if you are using your digital work software to see how this counting is happened, but if you observe their frequency of operation, or the way which they generate the output, then and only then you can able to compare that the synchronous counters are a bit faster compared to the asynchronous. And the design is also there is slightly difference we can observe here, and that will also decide that how the successive flip-flop will perform their toggling. Okay, so let me first draw, just because we are now going to discuss the 4-bit series of counter. So let me first draw the 4T flip-flop. Okay, am I audible?
Yes, sir.
Okay. So let me say this is my first T flip-flop, and of course in every T flip-flop we have some inputs. So this is my T input. Outputs means Q and Q bar, and we also have one clock terminal like this. And let me duplicate it. So this is like this. This okay. So these are the 4T flip-flop we have taken, and somehow we have to follow that same thing which we have written in the previous slide. So first of all, we have to provide a common clock pulse. So let me take it in this way. This is a common clock. This is a common clock applied to all flip-flops. Okay. This is clock. Let me write it here. This is clock, and you have to apply the input to only the first T flip flop, and this must be operated in toggle mode. Okay. Hello.
Yes, sir.
So to operate in a toggle mode, what logic you have to apply over here? Logic 1.
Logic.
Yes. And interestingly, what happened that the next flip flop will be operated by, मेरी बात ध्यान से सुनिएगा, यहाँ पर अगला फ्लिप फ्लॉप का जो इनपुट है वो पहले फ्लिप फ्लॉप वाले आउटपुट से ऑपरेट होगा, दूसरे वाले फ्लिप फ्लॉप का जो इनपुट है वो पहले और दूसरे वाले फ्लिप फ्लॉप दोनों के आउटपुट से ऑपरेट होगा, तीसरे वाले फ्लिप फ्लॉप का जो इनपुट है वो पहले वाले जो तीनों हैं उनके उसके आउटपुट से ऑपरेट होगा. तो इंटरेस्टिंगली इस डिजाइन को किस तरह से बनाया जाए, क्योंकि कहीं ना कहीं जो पहले जो रिपल का जो फिनोमेना था क्लॉक का वो यहाँ से खत्म हो जाएगा, और जैसे ही पहले फ्लिप फ्लॉप का कोई ट्रांजिशन होता है एट द सेम टाइम ऑलमोस्ट वेरी इन अ वेरी लेस प्रोपोगेशन डिले ऑल द फ्लिप फ्लॉप विल एबल टू चेंज देयर आउटपुट स्टेट. ओके, and to do so what we have introduced here, we actually connect our series input and output of these flip flop like in this way. Here we connect first, then to connect second, let's take one D AND gate. And in this AND gate actually, mm, I need some more spacing between this. So what to do? Let me take it this way. Take this, let this out, and this. Am I audible?
Yes, sir.
And my board is visual. Yeah.
Yes, sir.
Oh. Okay. All right. So just try to observe what is happening in this next flip-flop input connectivity. We provide this connection in this way. First of all, these two inputs of the previous flip-flop, okay, will go to the input to an AND gate like this, and then this output will drive the next flip-flop input. Okay,
Yes, sir.
it is clear.
Yes, sir.
And similarly, because two outputs of the previous flip-flop will be available here, and if we, for example, we want to drive it here, then of course in this case this output will connect to the next flip-flop, और previous all output दो यहाँ पर है और एक यहाँ से ले लेंगे, तो I'm going to connect in this way, like this. This is one connection, and this is the another connection. You can take separately from all the flip-flop, or you can do it in this way, just because AND gate is following the associative law also, so we can do this connection in this way also. Okay. Okay, so these are actually the AND gate which we are using here. These are AND gates. AND gates. Okay. Now let's try to means write down the transition condition, state transition condition, when these flip-flop will take perform transition. Okay, or before that you can also write this is, let's say this is T0 Q0 Q0 bar, T1 Q1 Q1 bar, T2 Q2 Q2 bar, this is T3 Q3 and Q3 bar. So let me write now the state transition condition. State transition condition means when they change their state. So let me write the first. So for example, this toggle input is applied to the first T flip flop. So for every clock pulse, the output will toggle accordingly. Yes. Hello.
Yes, sir.
So what I can write? I can write in this way: this Q naught output is toggles on every clock pulse, on every clock pulse. Okay. Now second, when your Q1 toggles, tell me, your Q1 toggles,
2 clock.
when your Q1 toggles, when when your Q naught is equal to 1, yes, hello,
Yes, sir.
and you can also monitor at the same time because clock is also applied, and the clock is applied. So when both the sync together, they will change its state. Similarly, if you move on to the Q2 toggling state, then the Q2 toggles when Q1 and Q naught together will have a combination like is equal to 1, and of course clock will be present. Clock is applied. And similarly, the Q3 toggles when Q2, Q1, Q naught is equal to 1, and and clock is applied, okay. So this is the entire functioning. Now let's also uh, means draw or we can say write the state transition table. State transition state transition tables. Okay. Am I audible? Hello.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay.
Yes, sir.
So let me take in this state transition table. Our columns are like we also include clock. So let me write in this way. This is, let's say this is clock. Then we have to write the outputs. So this is, let's say, my Q3. This is my Q2, Q1, and Q naught. Then you can write the decimal equivalent also, so that you will get an idea that how this counting take place. Okay. So earlier, for example, if we do not have any clock, okay, let's consider the first click. In absence of clock, what will be the output? Output will be all reset. Let's say 0, 0, and 0. Okay. Hello. Hello. Hello.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
When the first clock comes into the picture, then it will start counting. Okay. So this will be 0, 0, 0, 1. When the second clock comes, then it will count second, means 0, 0, 1, 0. Okay. And then when the third is come, it will 0, 0, 1, 1. For the fourth clock, 0, 1, 0, 0, 5, 0, 1, 0, 1, 6, 0, 1, 1, 0, 7, 0, 1, 1, 1, 8, 1, 0, 0, 0, 9, 0, 0, 1, 10, 1, 0, 1, 0, 11, 1, 0, 1, 1, 12, 1, 0, sorry, 1, 1, 0, 0, 13, 1, 1, 0, 1, 14, 1, 1, 1, 0, and 15, which is 1 1 1 and 1. Okay, so in this way, this is you will have a counting sequence which will start from this is 1. Okay, this is the counting sequence, and after that, for example, if 6 15 16 17 18 up to next state, then what happened? For example, if you have 16, then it will restart again. Okay, hello, 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 am I audible?
Yes, sir.
Okay, so you can write
Yes, sir.
this counting like this. This is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 0. Okay, so in this manner, this counting by following this counting sequence, this is also known as your mod 16 counter, mod 16 synchronous counter, you can say. And just because this is counting with, in a upward fashion, so you will write it as this is up counter, this is up counter. Okay, and at the same time you can also take one note. एक मिनट होल्ड करना. हेलो, हेलो, नमस्कार. अभी मैं थोड़ा सा बस बिजी, मुझे आप 15-20 मिनट बाद फोन करेंगे क्या, या एक से दो के बीच में फोन कर लीजिए मुझे. मैं हाँ 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 हाँ, मैं ही मिला. हाँ, ओके ओके. What this point? Hello, am I audible? हेलो.
Yes, sir.
तो ये अप
Yes,
काउंटिंग के
sir.
लिए, तो अगर मान लो कोई आपसे कहे कि डाउन काउंटर बना दो भैया, तो आपको करना क्या है कि जो अभी पहले वाले डायग्राम में यहाँ पर आपने सारे जो ट्रांजिशंस जो दिखाए हैं, है ना, एंड गेट के, वो किससे कनेक्ट किए हैं? क्यूज से कनेक्ट किए हैं ना. हेलो.
Yes, sir.
और अगर आपको डाउन काउंटिंग करना हो तो यही सारे कनेक्शन आप किससे कर देना? क्यू बार से.
So, Q bar, sir.
क्यू बार से, बस बात खत्म. Simple. Okay, so the note point, write on the note point, to construct a down counter, simply connect Q bar as input to the next stage. Okay, hello.
Yes, sir.
So now interestingly, we also have to do a comparative analysis in more technical fashion. Means how we can say this is a less transitions in this manner. For example, let me write in this way: in an n bit series counter, the TCLK must be greater than or equal to the TPD, the propagation delay of the flip flop, एंड प्लस यहाँ पर क्या हो गया, दो और एंड गेट जुड़ गए थे ना, तो n-2 TPD ऑफ किसका, एंड गेट का। तो जो क्लॉक फ्रीक्वेंसी है, अब वो उसमें दिस इनइक्वालिटी मस्ट होल्ड फॉर प्रॉपर ऑपरेशन। ओके, फॉर प्रॉपर ऑपरेशन दिस इनइक्वालिटी मस्ट hold. Okay, and of course the reverse part you can also write. For example, if you want to know the frequency of the clock, then FCLK must be less than or equal to 1 upon TPD of each flip flop plus n-2 TPD of 2 AND gate. Now interestingly, what you can observe here, that we do not mention the AND term. Hello, in with the TPD. Yes. Hello. Hello.
Yes, sir.
So we
Yes,
do
sir.
not the product and term associated with this. Okay, but only the product n-2 product term will associated with the, which has been introduced with with a two additional AND gate. Okay, so what we can say that the dependency of two propagation delay has been reduced in this case. So let me write in this way, that the time period is dependent on the number of flip flop stages, first point, and this problem is resolved. This problem is resolved in parallel counter. Okay, so how much time we have left?
7 minutes, sir.
7 minutes. Okay, so in the next lecture we will discuss the 4-bit parallel up counter, and in which we will see that this n factor is gonna completely remove, and when this n factor is completely removed, then no matter how many flip flop you are using to design a counter, that will be independent of number of flip flops. So in that case, this clock frequency will be drastically increase, and when this increase, then the overall counting process will become